Hello, this is mathjazz from Almost Cool. I have here a slower speed of light. This game was put out by the MIT Game Studio, I think is what it's called. Let's check. Let's see. MIT Game Lab. That's the name. So the point of this game is to kind of give intuition on what Lorentz contraction and other relativistic effects are. This game is, well, okay. So it's super short, and I mean, like, it'll be less than 5 minutes to beat this whole game, but it's uh it's a wonderful, I think, exercise in getting some intuition on what near light speed travel might look like. The faster we go in this game, the more relativistic effects will be shown on screen. It's pretty cool. That's pretty fun, and we'll have more on the science of it after we play the game. They have some excerpts about the physics behind what's going on here. So I'm not going to speak a whole lot for the rest of the game itself. We'll just experience the game. Okay, so um, let's click on the What Happened tab, and we'll see the excerpts that they've written about different effects that happened in the game. Make everything as simple as possible, but not simpler. Albert Einstein. In a slower speed of light, the speed of light slows down with every orb you pick up. It's impossible for you to reach the speed of light, but certain relativistic effects become more visible as you get close. Light behaves like a wave, and different wavelengths appear as different colors. As you and other objects move around, the wavelength of light changes, appearing redder or bluer to your eyes. Some light becomes infrared or ultraviolet, which your eyes cannot usually see, and other invisible sources of light will become visible. So, for example, let's say that, and I'm pretty sure that the game does this, but I'm not certain. But in let's say that all of the plants and they don't look like animals or people, but there's the things that were moving around. They're living things, and so they produce heat, and so that also means that they're going to produce infrared light, which humans normally can't see. As you're moving toward one of these objects at relativistic speed, you're going to see all of those wavelengths shrink. So some of the visible light, maybe all of the visible light, becomes ultraviolet and above and becomes invisible. And then the infrared light, some of that becomes visible light now, because the too long wavelength of the infrared gets compressed enough to become in the visible spectrum. So that's part of what we were seeing when the game was playing, I think, is what normally would have been infrared light radiating off of the different plants and things, becoming visible as we are traveling towards it at relativistic speed. Now, I didn't try backing up in the game, but if we were moving away from an object that was producing ultraviolet, if we're moving away fast enough, then that ultraviolet would be stretched out until it's wavelength is long enough to be visible to us. Now, I don't know if there's anything in the real world that produces ultraviolet. Well, obviously there are things that produce ultraviolet because ultraviolet is a thing. But I don't know if like living organisms give off ultraviolet the way that they give off infrared, or if maybe, I don't know, maybe radioactive rocks give off ultraviolet. Maybe bugs give off it. I know that some bugs can see in ultraviolet. Anyway, so if we were moving away from an ultraviolet source fast enough, then that normally invisible light might become visible. So this is something that you guys saw a lot during that gameplay. As I was turning, you'd see the searchlight effect. So let's see. Light also behaves like a stream of particles called photons. When you run toward a stream of photons, more photons hit you, and the object becomes brighter. This effect is also known as relativistic aberration. Special relativity. Light always moves at the same speed, so if the speed of light is constant, then the distances and times in the world around you have to warp. Your time is different from the time in the world, time dilation, and your distances are different from the distances in the world, Lorentz transformation. You have to be much closer to the speed of light to notice the more dramatic effects of Lorentz transformation compared to the Doppler and searchlight effects. At the end of the game, the Doppler and searchlight effects are removed to make the Lorentz transformation easier for you to see. That's what happened the moment we collected that 100th orb. A cute little comic down here. Normally, light is extremely fast, but it still takes time for photons to reach your eyes. When you look at anything, you are actually observing incoming light from some time in the past. The farther you look into space, the further you look into history. This is easily noticeable when you look at objects moving relative to yourself. Objects normally beyond your field of view can become visible when you move near the speed of light, as you see them as they were in the past. And then the cute comic about a photon that's running up to a person saying, "Lincoln's been shot," and then the person responding, "Photon, for something so bright, you sure are slow." Meaning that light still takes time to get places, and seeing light that's come from a long way away means that you're seeing light that's been produced a long time ago. They have acknowledgments to some corporate sponsors and to a lot of physics papers, and most importantly, an acknowledgement to Elektrodynamik bewegter Körper from the Annal of Physics in 1905, Albert Einstein's paper. This might be the paper that he won the Nobel Prize for. The title of the paper that he won the Nobel Prize for in English is The Photoelectric Effect. I'm not sure how that translates into German. I feel that it's not. He wrote 4 papers that year. One of them was the relativity paper, one of them was on Brownian motion, one of them was the photoelectric effect, and maybe either this one is the 4th, or this is the German name of the photoelectric effect paper. I think that this is the 4th paper he wrote. Let's see. The 4th one is math's energy equivalent. So this here is the photoelectric effect paper. Okay. Oh, no, no, no. I am completely wrong. This is the title for the special relativity paper. So in English, the paper is called On the Electrodynamics of Moving Bodies, sometimes just called Special Relativity. And, okay, yeah. Electrodynamics between bodies. Okay. So this is the special relativity paper. Anyway, thanks for watching me play this game. It is free at MIT's website. Link will be in the description of the video. And I hope you guys have a great day. Bye!